And is there any questions? Let me open up this so that way I can see everyone.
Okay, please join me in thanking Spenser. So there was a question in the chat line.
Oh, I see it.
And maybe you can verbalize the question and show the equation that it was about.
Yep. So the question from Dr. Svetlana is, what is the omega for the in the P up and the P down terms of the Hamiltonian? So let's head back here. This was the slide you were wondering about, correct, Dr. Svetlana? Yes. So the omega is the wave packet speed.
How sure you are?
So wave packet is what you motion, right? So you're trying to say that this is kind of a momentum of electron?
Yes.
Well, I actually opened your the report, which was also done by you, I guess. And there is more information on this value, and actually it's represented. My understanding is represented in the different way. Yes, it is K. It corresponds to the K, but this K, is it really a momentum or something different?
Just forget everything from the course and analyze it mathematically. Next slide. The one with, yes, top line. Yeah, the V up equals delta E plus M omega squared and then X minus X up. Can you point it by the marker? Yes. So mathematically, which curve it is?
This is going to be the solid black curve.
Okay.
And what is the meaning of this V up and V down in your in the Hamiltonian? Like when can you go on the previous slide once again? Yeah. So you're showing T plus V up. What is V up? What is T?
T is the
which terms contribute to the Hamiltonian?
To the Hamiltonian, we have these two V up and V down. For the Hamiltonian, we have the H up and the H down. We have these four terms.
But in general, how you construct Hamiltonian in general? What terms contribute?
Which kinds of total of energy contributes to total energy?
I couldn't hear that from you, Dimitri.
Which kinds of energy contribute to the total energy operator?
What kind of energy? It would be energy that is in the atomic units. Alternatively, it could be, or it can be also listed as EV.
Okay, I will. In general, how many types of energy do you know?
There are a few.
Can you name them?
Sure. There are volts. There are
the types of energy in general.
Oh, heat energy.
No.
Heat is not the energy. Heat is a way how the energy transfers from one way to another way. Heat is not the energy.
Okay.
What kind of energy you know? If there is a motion, then
kinetic energy.
Okay, so you have kinetic energy, which defines the energy of motion. And are there any other types of energy?
There's potential
energy. What does potential energy tells you about? Or what kind of?
It tells us the if the
if there's an interaction, right, between something. So then it looks like your T and V up probably stays for these different types of energy. One is kinetic, and T usually is used for the kinetic energy. And you use this V up and down. This is for potential energy. So then the energy of electron, the motion of electron should be really contributed to the kinetic energy, not to the potential energy. Do you agree? Okay, then
Yes.
return back to the form of your V up and V down. Next slide. Yeah. So take a close look and think about then what exactly we have here for this term and what this mw square over 2 stays for. This is x square, right? You can say x minus x naught square times, there is some coefficient usually when you present this type of potential energy.
So mathematically, which type of curve does this equation represent? Like circle, straight line, or something else?
It's going to represent a parabola.
So what is the center of parabola and curvature of parabola?
The center of the parabola is going to be this right here. Actually, sorry, in the V up, it's going to be the delta E. In the V down, it's going to be this. Because the center of the parabola, or not the center, the parabola-like curve is going to be as denoted here.
It's not only the center of parabola, but you also have the curvature of parabola, right? So then
yes.
What corresponds to the curvature of parabola?
These two.
Parabola.
Well, if you look on the D up, I think this is easy to see for the D up.
What represents the curvature of the parabola? It's going to be this.
So actually, your omega not really depends on the velocity of your electrons, which actually contributed into the velocity of the wave packet. It is this omega. Yes, the whole term can be called k, which is we call a spring constant, right? Because if your potential energy is just a parabola, then its curve would be kx squared over 2, whereas k is, you can think about as the same shape as it would be the potential energy for the spring, which is going, you squeeze it and then let it go, right? So then it is really the Cook constant. And I think in your text, in your report, you were explaining that this parameter was taken based on the calculations from density functional theory calculations, atomic level calculations, which really provides you this information about the strength of the bond inside your material, because this potential is really due to the nucleus, and it really depends on a lattice structure of these perovskite systems and the way how these all atoms are interacting with each other. Right? So technically your electron is moving feeling the potential from nucleus, and somehow you represent this interaction through the parabola, through the parabolic, through the how we call it, harmonic oscillator approximation for the potential energy.
And you could answer the question of Professor Killian with one word instead of this half an hour discussion. So letter omega is in harmonic oscillator is typically stands for how frequent it goes forward and backwards, right?
Right.
Which means the word that starts with the letter F.
Yeah. Frequency. Spenser, you're killing me, dog.
Frequency.
Yes, perfect. Okay, the question is answered. And there is one more question.
It's not a frequency of electronic motion, am I right?
Correct.
It's a frequency of motion of nucleus in your system. So this potential contributes to the really nucleus motion of your system, which electrons feel as a potential and move in this potential.
Mm-hmm.
So there is one more question typed in the chat line. Spenser, can you read it and answer?
The question was, I thought we already answered that. You have the harmonic oscillator question mark what is the allowed energy? That's at least the last question I have.
Mm-hmm.
Okay. So the allowed energy, let me get back to my PowerPoint. The allowed energy is going to be coming into play here, I believe. Because it doesn't have a place.
Spencer, the question is purely academic, irrelevant for your research. Just what are the allowed energies for harmonic oscillator? It's more like a question for the class.
Think about what is the lowest energy is possible.
0.
Isn't it correct? Think twice.
Think about if n equals 0, the very low state in the harmonic oscillator, does the energy really 0 or not?
No, it gets closer and closer to 0.
But how you can express this energy of the lowest state in terms of your frequency omega? And it was a recommendation, at least as a one equation to memorize from the course.
It would be from Schrodinger's equation?
Solution of Schrödinger equation. Eigenenergy for lowest state of oscillator.
Mm-hmm.
Do you remember the formula? Yeah, for the energy in the of the electron of the particles in the harmonic oscillator. It is quantized, right? N goes from 0, 1, 2, 3, 4, any integer numbers, and the energy H nu.
If you look to the booklet,
H omega over 2, wherever you prefer to.
the booklet, page 7 from Zane, has a graphical illustration of this concept.
Let me get that up. Give me a second.
I will post it differently. So do you agree that the energy in the harmonic oscillator quantized? Means that you will have discrete levels, right? Do you agree with this?
Yes.
Then next question is, what is the splitting between each of these states?
What is the what?
The energy splitting, the difference between each of these states.
The difference between these two states?
Well, in any harmonic oscillator, right? You have
It's going to be the difference between the ground state and the excited state.
which equals to what? Do you remember the formula for this?
Yeah, it's n plus 1/2 times h bar times w.
Perfect.
Energy when n goes from 0, 1, 2, 3, 4, and if you take a splitting between two levels, let's say the ground and the next one, this would be just h nu or h omega over 2, h nu over 2 or h omega over 2, depends whether you use h bar or just regular h.
Mm-hmm.
And the splitting will be exactly the same between all states. So they are equally splitted, and the lowest energy is h omega over 2. The next would be just h omega. The next one would be, again, plus another h omega over 2, and so on, so on. So each of them splitted by h omega over between each of these states.
I think there is a consensus on this question. Does anyone want to learn more from Spenser? If no, please join me in thanking Spenser for presentation and for great answers.